Another equation is when the Grashof number is less than or equal to 0.15 times the square of Reynolds number. It demonstrates that the impact of buoyancy on the local heat transfer coefficient of pure force convection is less than 10%. When the buoyancy-induced flow and the force flow goes in the same direction, the left equation is pertinent if the pure natural convection behavior is less than 10%, and on the right equation, it applies from forced convection behavior by less than 10%. The figure on the left shows the laminar zones of forced, mixed, and natural convection for heated vertical plate in a horizontal forced flow, and the figure on the right shows the turbulent zones of forced, mixed, and natural convection for heated vertical plate in a horizontal forced flow. And finally, this equation is for the approximation of the Nusselt number for combined forced and natural convection. For vertical plates, where the flows are in the same direction, n is equal to 3, and addition is done to the force and natural Nusselt numbers, while subtraction is done when the flows are in opposite directions. Now let's move on to our next topic, which is the fin tube bundles in cross flow. The heat transfer coefficient for gas flows in tubes is quite low, so there is a requirement to apply improvement methods in the cross flow over multi-tube bundles. Increasing the surface area or the convective heat transfer coefficient will reduce the thermal resistance that appears in the flow over tube bundles, which can be manifested using the equation of convective heat transfer. This equation can be utilized to calculate for the pressure drop and heat transfer, where St is the transverse pitch and Sl is the longitudinal pitch. And also, the Reynolds number can be equated from this equation. Friction loss can also be seen in this equation. The pressure drop can be computed by applying the Euler's number. Cz in the equation is the correction factor for tube bundles, with the NL value of less than 5, which can be established through the table shown. The flow of inline tube banks with circular or helical fins have a fin surface extension ratio, and the Euler's number can be equated in this equation and is limited with these conditions.